here is an example where we have non-uniform circular motion. So I'm going to start by drawing a free body diagram, and to do that I'm going to draw a picture. I'm going to look at a bird's eye view. Okay, so here is this steel block. It's spinning around in a circle. This is the long arm, okay, and it's going at 200 RPM. And it says once the motor stops, so that means that nothing is pushing it forwards anymore. How long does the block take to come to rest? So we're going to come to rest because there's going to be kinetic friction. The kinetic friction is always going to point opposite the direction we're moving, and since we're always moving tangent to the circle, the kinetic friction is always going to oppose that and go in the opposite direction. So there is a force in our tangential direction. Whenever you have a force in your tangential direction, your speed is going to change, and that's what's happening in this problem. So this is not uniform motion because our speed is going to change because we have this force in the tangential direction. So I'm going to just look at the bird's eye view for this for now, and I'm going to say that going straight down from this perspective is my positive tangential direction. My positive R direction is going to the right. And I'm just looking at while there's friction, while it's coming to rest, while it's slowing down. Okay, so while it's slowing down, if the object is traveling, in this counterclockwise direction, I'm going to have kinetic friction going in the negative tangential direction. In the positive R direction, I just have the tension in that arm, whatever that is. I don't know. In this problem, it actually doesn't even matter. From a head-on view, this would be the steel block coming out of the page, out of the screen towards you. Okay, so now the tangential direction is coming out of the page. In this perspective, I forgot to mention the Z direction was coming out of the page. Now the tangential direction is coming out of the page. So I'm not going to show any of the forces in the tangential direction. Just like here, I did not show the force of gravity and I did not show the normal force because those forces are in the Z direction. And from a bird's eye view perspective, you don't show the Z direction. From this head-on view, though, I do show the Z direction, and it's the forces in the tangential direction I'm not going to draw. So in the positive Z direction, I have the normal. In the negative Z direction, I have mg. And then again, I have this tension in this arm, whatever that might be. So I'm going to look at my net force in the Z direction. It's N minus mg. I'm not accelerating in the Z direction, so my net force in the Z direction should be equal to 0. That lets me say that N is equal to mg. No surprise here, right? You probably could have figured that out on your own because this is one of those very typical cases. I'm going to look at my net force in the T direction because the net force in the T direction is going to determine my acceleration in the T direction, which will determine the rate that I'm slowing down. I'm not going to look at the net force in the R direction because it doesn't really matter to me. If the problem had said what was the tension here, at some later point in time, then I am wondering about this tension and I would care about that. But in this problem, all I really need to know is how long does it take? And how long does it take? That's quite asking a question about delta T. So you can think delta T, that's a kinematic variable. So I need to know my acceleration in order to use kinematics. And then you might think, well, which acceleration am I talking about? Well, I'm going from some initial speed to a final speed of 0. So I need to know that like tangential acceleration there, not the centripetal acceleration or the radial acceleration, because that's not going to tell me how fast my speed is changing. This tangential thing is telling me how fast that's changing. So my net force in the T direction is just in the negative T direction, I have the force of kinetic friction. My net force in the T direction is always equal to my mass times my acceleration in the T direction. And my force of kinetic friction is always equal to mu sub k times my normal. And we already said that our normal was equal to mg, so this becomes mu sub k times mg. And you can see that my mass cancels. So I cancel out my mass, and I can say a sub t is equal to negative mu sub k times g. And here I've plugged in for mu sub k and g, and I get my tangential acceleration is negative 5.9 meters per second squared. So that's my tangential acceleration. If I could now figure out, actually I think I might want to do this in terms of angular variables. Let's figure out the angular variables here, just because it's extra practice. You could do this in terms of v sub t initial, v sub t final, and a sub t. That's fine, but I'm going to do it in terms of my angular variables. So I'm going to convert that 200 RPM, which is 200 revolutions per 1 minute. I'm going to convert that into radians per second. First, I cancel out the minutes by saying 1 minute is 60 seconds. And then I cancel out the revolutions by saying 2 pi radians is 1 revolution. So the math that I would do would be 200 times 2 times pi divided by 60. That gives me 21 radians per second. That's going to be my initial angular velocity. That's the rate that I'm rotating at initially before the motor turns off. My final angular velocity is just 0 because I come to rest. I'm going to figure out my angular velocity by using my tangential velocity is negative 5.9. So my tangential velocity is always equal to my angular velocity times r. That's what I've done here. So I get that my angular velocity is equal to minus 7.4 radians per second squared. And now I know the value of 3 kinematic variables. That's going to let me solve for a 4th kinematic variable. So that's my delta t. So now I can choose the equation that involves those 4 variables. Here's the equation. And here I've plugged in the numbers, and here I've solved for delta t. Now, like I said, you could do everything in terms of tangential variables. So you could use this as your a sub t. You could find v initial, v tangential initial by saying, converting between omega initial and v sub t, just multiply this by r. Then you would get v sub t initial. V sub t final would still be 0. You already have your a sub t. You choose the same equation, and you would get the same answer.